This is AP Calculus AB, and in this video, I'm going to talk about section 8.3 volumes. This is actually the last section of new material that we're going to cover in this course. And I will warn you that there's a lot of material in this video, and also just let you know that we're going to spend several days on this because this is a concept that people tend to struggle with a little bit at first. The whole idea, though, always boils down to one simple setup. And if you can get that in your mind, the concept of volumes becomes fairly simple. So let's take a look at the idea here. So the idea is we're always going to break our volumes into cross sections. And then what we're going to do is we're going to stack up a bunch of cross sections that have a very, very thin width. And that's going to create our volume. And so really what we're always going to be doing is we're always going to be looking for the area of that cross section. And once we know the area of the cross section, this is how we're going to find the volume. So we're going to integrate from A to B. A of x dx is essentially going to be a very, very thin slice of our volume. We have the cross section area, and then dx gives it a thickness, and then the integral is going to add up all of those pieces over the interval that we're looking at. Okay, so if you can get that through your head, like I said, this becomes a fairly simple idea because all we're really doing every time is we're trying to figure out what does our cross section look like? How do we find the area of the cross section? Once we figure that piece of it out, the rest of it kind of takes care of itself. So I wanted to show you some animations here. Okay, so the first type of a volume that we're going to look at is what we call just a volume by cross section. Now, really, all of the volumes we're going to do are volumes by cross section, but these ones are going to have defined cross sections, as in the problem will tell you specifically use this type of cross section. So here's an example. Find the volume of cross sections perpendicular to a fixed diameter of a circular base are squares. Okay, so we have this base, and the hardest part of this is always going to be visualizing what they're describing. So what we have here is a base that's a circle. And what we're going to do is we're going to stack squares on top of this base. And essentially the squares are going to come out of the screen. So I did this in Geometer Sketchpad because I wanted you to be able to see more of a 3D rendering of what we're trying to look at here. So if we were to kind of visualize what these squares look like, what they're going to do is they're going to line up perpendicular to the x-axis, and then they're going to go from the top of the circle to the bottom of the circle. They're going to come out of the screen. So here's essentially what we're looking at. We've got these squares coming out of the XY plane. And so then they've got a height. Well, they're squares. So if I think about the area of the cross section, the distance between the top and the bottom of the circle is the length of one side of the square. And then I can just square that, and that would give me the area of the cross section. So essentially, like I said, what we're going to do is we're going to give each one of these squares here a really, really thin thickness. Since we're perpendicular to the x-axis, the thickness of that cross section would be dx. And in the end, this is how we're going to create it. We're going to stack all of these squares going across this base. So that's essentially what's going to happen. And you can see in the end here, let's actually create the solid. This is how the solid is going to be created. And notice down here, I've got this integral. And what this program is doing is it's taking these squares and giving them a really, really thin thickness for dx. And then it's just adding them all up as it sweeps across this base. So in the end, this is what it looks like. Now, knowing what the three-dimensional shape looks like for our volume calculations is not really that important. What really is important from a calculation perspective is going to be, what does the cross section look like? If you know what the cross section looks like and know how to find the dimensions that are important for that cross section, then this becomes fairly simple. And here's just another view of that. So there's the 3D figure with those squares sweeping inside of the 3D figure. And again, you can see as we're sweeping across, our volume is increasing as we add each of those squares with a really, really thin thickness. Okay, so that's what we call typically a volume by cross section. Okay, so going back to what we were looking at here with our general setup, you can see this volume integral now makes a little bit more sense, right? We've got all of these cross sections with a really thin thickness. The integral is going to add them up. So let's take a look at an example that's already been worked out. It says place a square pyramid so that its vertex is at the origin and its altitude of 3 meters lies on the x-axis. Find its volume if the base measures 3 meters on a side. Okay, so everything's sort of been done here, so this makes this a little easier. But the idea is I've got to figure out what my cross section looks like. And you can see here, we've got this pyramid that has its altitude in the x-axis or on the x-axis. And my cross section, we're calling x by x. So the dimension of the cross section then is just x squared, or the area of the cross section, I should say, is x squared. The thickness is just going to be the distance. If I'm thinking about thickness, I'm thinking about, okay, if I go from here to here, how thick is that really thin cross section? And we're giving it a very, very small thickness of dx. So each one of these ax times dx's is a small piece of volume, and then the integral adds them up. And you can see the integral solution itself is fairly simple. We just had to do an antiderivative and we get 9 meters cubed. Well, this is a figure that we actually knew how to find the volume of using a formula, right? So we know how to find the volume of a pyramid. It'd be 1/3 times the area of the base times the height. Well, you can see here, if I look at the base of this, the base is a square that's 3 by 3. That would be 9. The height was 3. That would be 9 times 3 is 27. Take 1/3 of that, you're going to get 9. So you might think, well, I already know how to find the volume of this type of a figure. Why would I ever do this with an integral? Well, the idea is this is actually where all of those volume formulas come from. So when you know the volume of a sphere or the volume of a pyramid or the volume of a cone or the volume of a cylinder, all of those formulas are derived using these simple calculus techniques. All right, so here's another example. It says, let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs of y is equal to sine x and y equals cosine x as shown in the figure above. So just like when we were dealing with the areas, sometimes they're going to give you the graphs, sometimes they're not. When they give you the graph, it makes this a little bit easier because I can see exactly what I'm trying to do to set this up. Okay, so we want to find the volume of the solid whose base is R and whose cross sections cut by planes perpendicular to the x-axis are squares. So when you first start this, you might want to actually draw your cross section. So I'm going to draw this cross section of a square, and then I'm going to label its dimensions, because this really reminds me, this is what I'm trying to do, is I'm trying to find the area of that cross section. So remember, it said they're perpendicular to the x-axis, and the distance that I want is going to go from here to here. So it's sort of like when we did areas, right? I have the upper function minus the lower function. It's going to be the length of the side of that square. So if I do cosine x minus sine x, that side that I had drawn there, you can think of that as the same thing that I have right here. So that dimension is going to be cosine x minus sine x. Since this is a square, this dimension would also be cosine x minus sine x. So for the area of my cross section then, this is pretty simple. It's just cosine x minus the sine of x squared. Okay, so now I need to give each one of these square pieces a thickness to create a volume. Since I'm perpendicular to the x-axis, the thickness of my square is going to be dx. So for the volume then, all I have to do is add up all of those pieces. I'm going to come back to the limits of integration in a second, but I know that I'm going to use my area, cosine x minus sine x, and then I'm going to multiply, or I'm going to square it because it's a square, and then give it a thickness of dx. And now I just need limits of integration. So for the limits of integration, go back up to this figure that they gave you. Notice we're starting obviously at x is equal to 0 here. Then we have to find this intersection point. Well, cosine x and sine x, if you set those equal to each other, they have the same value at pi over 4. So just using some unit circle values there. So I know this integral is going to go from 0 to pi over 4. Okay, so there's my setup. Now, when we solve these out, we're not going to spend a lot of time really talking about how do we solve these integrals. Most of the time, we're just going to plug these into the calculator, or you're going to have very simple integrals that you can solve out by hand. But as I go through them on the video, I'm not going to focus on the integral solution methods because that's not really the focus of what our lesson is. The focus that we're trying to really emphasize here is the idea of setting up these integrals to represent the volume. But if you did plug this into the calculator, you would get a volume of about 0.285. And just a reminder, when you plug these things into the calculator, when you have calculator active problems, try to use at a minimum 3 decimal places. Okay, so the main idea there, though, is fairly simple, right? We got the area of the cross-section. We gave it a thickness. We used the integral to add up all of those pieces. Okay, so now here's where this is going to change a little bit. The next thing we're going to look at is called a volume by revolution. So I'm going to go back over to my Sketchpad animations, and I'm going to show you the difference between what we just looked at and what we're going to look at now. Okay, so this is going to be what we call a volume by revolution. So for a volume by revolution, what we're going to do is we're going to go through and we're going to take some region and we're going to revolve it about an axis. So when we do that, we're going to have different cross sections. We're still going to end up doing the same setup. We're going to have the area of the cross section. We're going to give it a thickness. We're going to add up the pieces, but our cross sections are going to change a little bit in this case. So let me show you what happens here when we create this. So we've got this region here that's been defined. It's square root of x. It looks like we're going from 2 to 9, and I'm going to revolve this around. So we're revolving about the x-axis. Now, take a look at your cross-section here. The cross-section in the middle is really what's important. So even though I have a different way of kind of visualizing the way the volume was created, I still have, in this case, a cross-section that's a circle. And then I'm just going to give that circle a thickness of dx. And in the end, the way that I find the volume, it's still going to be the same. I have all of these little thin discs of volume that are going to be stacked up to create that overall shape. Now, you might think, okay, I want to visualize what this three-dimensional figure looks like. And you can do that. It's fine. If you can visualize the 3D figure, that's great. If you want to sketch the 3D figure, that's great. But the important part is, what does the cross section look like? That's always going to be what we have to think about when we're setting these up. Okay, so we'll come back to this animation in a couple of minutes because we're also going to do some volumes by revolution and get a different type of cross section. All right, so let's take a look at this example that we have here. It says the disk method. And I don't really like to switch between a volume by revolution and a volume by base because to me, they're all going to be volume by cross section. But what I'm going to do here is I'm just going to call this the disk method temporarily so that you can see that, yes, the creation of the disk is slightly different, but in the end, it's still a volume by cross section. So we're given this function 2 plus x cosine x, and it says take the region between this graph and the x-axis over the interval -2 to 2 and revolve it about the x-axis. Okay, so now this is where the visualization comes into play a little bit. So I'm going to show you on my calculator what this looks like. So here's 2 plus x cosine x that I've entered as my y1. I've got my window set to go from -2 to 2, and I'm going to graph this. Okay, so we're taking this region, and I can't shade on here very easily, but I'm taking this region that's between -2 and 2, between the x-axis and this curve, and I'm revolving it about the x-axis. So if you want to think about the shape of this three-dimensionally, it sort of looks like a vase, but it would be a vase that's filled in because it's going to be a solid volume. There's not going to be any empty space inside of this vase shape. Okay, so when I'm revolving this around, though, what I'm really thinking about is the distance between the x-axis and this curve, because I know I'm going to get some type of a circular shape anytime I do a volume by revolution. In this case, there's no empty space between my area and the axis I'm revolving around, so I'm going to get a solid disk of material for my cross-section. So going back to my calculation here, you can see they said the area of a slice of material here, or the area of a cross-sectional piece of material here, it's just going to be pi r squared. Well, the radius is the distance between the x-axis and that curve. So they did pi times f of x squared. Okay, so in the end, I'm still doing the same thing, right? I'm doing for my volume, I'm doing the area, the cross-sectional area, giving it a thickness, in this case of dx, and then we're going to integrate over whatever the region is. Our region was -2 to 2. That's what they defined in the problem. And then for our cross-sectional area here, remember it was pi r squared. Here's my pi. Here's my radius. The distance between the x-axis and the curve 2 plus x cosine x is 2 plus x cosine x. So I have pi times r squared, give it a thickness of dx, and then use the integral to add up those pieces, and that gives me the volume. So if you wanted to visualize, okay, what does the cross-section look like this time? Essentially what we're looking at here is, here's my cross-section, that's a circle. We've got this radius here, and the radius that I would calculate this time is 2 plus x cosine x. And again, when you first start these, you might want to draw these cross sections because it'll help you kind of clear in your mind, or make it clear in your mind what exactly is important from the geometry standpoint of the problem, or the geometric standpoint of the problem. Okay, so in the end here, again, we've got the setup. You're going to plug that into the calculator. And for our volume, in this case, I can't get an exact solution because 2 plus x cosine x, I'm not going to be able to solve that out. I'm going to get about 52.430 as my approximated solution there. So again, our main focus is the setup. Typically, once we get to that point, we're going to plug these into the calculator, but there will be some times where you're going to solve these out by hand as well. All right, so let's try another one here. It says, find the volume of the solid generated by revolving the shaded region about the given axis. And in this case, they say revolve about the x-axis. Okay, so this is actually from your textbook. And what I want you to do is I want you to try this one. So the region's already here. This line that's drawn in here is supposed to be essentially representing, when you revolve that around, that's going to represent your radius. So try to think about how you would set that up and solve it. So you can pause the video, try to set it up. Don't solve the integral out by hand. Just get the integral set up, and then you can just plug it into the calculator. Okay, so here's what I ended up with as my solution. You can see that they gave us this equation, x plus 2y is equal to 2. Well, I really need y in terms of x. So I went through and I said, okay, what's y in terms of x? Y is 2 minus x over 2. So that's my radius. Now here's my cross section. Again, it's a circle because I have all of this area being revolved about this axis, and I got a radius of 2 minus x over 2. So my cross-sectional area is pi times radius squared. So very simple geometry. And then the thickness here of each one of those slices is going to be dx. So I ended up doing it this way. I did pi times the integral from 0 to 2 of 2 minus x over 2 squared times dx. Now, notice I left the pi out here. And the reason I did that, it would be okay to put the pi inside of the integral. But the reason I put it on the outside is because I want to have an opportunity to identify if I do have an exact solution. So when I plugged this into the calculator, I plugged in the integral from 0 to 2 of all of this, 2 minus x over 2 squared dx, and I got a value of 2/3. So now I know my exact solution is 2 pi over 3, or 2/3 pi. So sometimes you're going to need to get exact solutions. And when you have a calculator available to you and you still want to get an exact solution, that's what I would recommend that you do. Leave the pi until the last step. Solve the integral out on the calculator, and then just remember, okay, whatever I got on the calculator, that times pi is my exact solution. Okay, so let's take a look at one other scenario that you might run into, and that's where we end up with something called a cross-section that is a washer. So I want to go back to my geometer sketchpad diagrams here, or animations here, to show you this in that 3D rendering first. Okay, so this is the exact same graph that we were looking at before, where we have the square root of x from 2 to 9 on the x-axis, and we're going to revolve it about a horizontal axis. But this time we're going to revolve around the line y equals -2. And the reason this is different than what we did before we revolved around the x-axis. So we had no empty space between our area and the axis of revolution. Well, when I revolve this around, there's going to be empty space that's going to be created in the middle of this. So let me show you what I mean. So you can see we revolve this around, and we've got this cross section that's in the shape of a washer. If you ever work with bolts, there's things called washers that are, you know, these little metal objects that look that exact shape, right? So they've got a circular shape, but then there's a circle cut out of the inside of them. So we call that a washer shape. Now, from a cross-sectional standpoint, we're still looking at circles, but the difference here is for my cross-sectional area, I have to do the outside circle minus the inside circle, and that gives me the region in between the two circles. But from the standpoint of how do I evaluate the volume, it still works the same way. We find the area of the cross-section, we give it a thickness, and then we add up all of those pieces going across the figure, and that's going to create my volume. So again, even though it seems like we're doing something different, we're still doing the same thing we were doing before. We're finding the area of the cross-section, we're giving it a thickness, we're using the integral to add up those pieces. Okay, so back to this problem. What if each cross-section is a washer? So we've got this region, the same region we looked at earlier. It's the region between the sine graph and the cosine graph between 0 and pi over 4. And what we're trying to do here is we're trying to find the volume if this is revolved about the x-axis. So let's start with a diagram here. This might make this a little bit easier at first for you to think about. So again, when you first do this, you might want to draw these cross sections out. So I know my cross section. Let me redo that inner circle there. I know my cross section is going to look something like this, right? So I'm going to have an inside radius. I'm going to call lowercase r. I'm going to have an outside radius. I'm going to call uppercase r. So I've got two radii here, right? So the region that I want to find is all of this stuff in the middle. So this is the cross-sectional area, everything in between those two circles. So I've got an r value here. The inside radius is that distance right there. So I'm going to call that sine x. The outside radius goes up to the upper curve, and that's going to be a distance of cosine x. So for that cross-sectional area, I'm going to do the outside circle minus the inside circle. So my area here would be pi times the uppercase r squared, or pi times cosine squared x, minus pi times sine squared x, because that's my pi times the lowercase r squared. So in the end, if you notice, if you were to factor the pi out of this, we just have pi times cosine squared x minus sine squared x. And now when we set this up in an integral, here's what the integral would look like. Our volume would be pi times the integral from 0 to pi over 4 of cosine squared x minus sine squared x dx. This is not one I would expect you to do without a calculator, but you could. We can use a trig identity and convert this into a cosine 2x. And then from there, we can actually solve this out and get the exact solution. So it turns out this is exactly equal to pi over 2. If you plugged this into the calculator, though, what you would do is just do this part of it. Forget about the pi for a second. Plug that into the calculator, and you would see that this is 1/2. And then it's just 1/2 times pi, and you get pi over 2. Okay, so again, fairly simple as long as you can figure out what the cross-section is supposed to look like. So same idea as before, slightly different cross-section. All right, so here's another problem that I want you to try. It says find the volume of the solid generated by revolving the region bounded by the lines and the curve about the x-axis. So in this case, we're bounded by y equals x squared plus 1 and y is equal to x plus 3. So you can graph this on your calculator if you want, or you can just sketch this. This is a very, very simple set of functions that you could sketch. But the main thing is I want you to try to set this up, and then you can just plug it into your calculator and get the exact solution using your calculator. Okay, so here's what you should have ended up with on this one. So x squared plus 1 is actually the lower of the two functions if you're thinking about the distance from the x-axis. So we have the region between x squared plus 1 and x plus 3. That's going to be revolved about the x-axis. So there's empty space between our region and the x-axis. So we know we're going to have washers. And you can see I found my two radii. I didn't draw the cross section this time, but I was just sort of visualizing what my cross section looks like. So eventually that's where I want you to get with this. So my inside radius here is the x squared plus 1. And then the outside radius, that's the longer distance from the x-axis, would be x plus 3. So you can see I found my cross-sectional area. And now I set it up here as an integral. Now, when you solve this out, all of this, remember, it's the outside radius squared. So this is my r squared, and this is my lowercase r squared. So I remember I'm doing the outside circle minus the inside circle. So always think about what's actually happening when you set these up. Okay, so when I plugged this into the calculator, I just solved this whole part out, right? Now, you may not recognize what the exact solution is right away, but you can actually have the calculator convert the decimal solution to an exact solution. So you can just say convert the decimal to a fraction. It'll give you 117 over 5. And then just remember you have to multiply that by pi. Okay, so again, fairly simple once you get the idea of this. And the idea is always the hardest part, or at least the setup is always the hardest part, because you've always got to be thinking about what does that cross-section look like? What is the thickness of that cross-section going to be? Now, there's one other type of problem that we need to look at, and that is when we start revolving around different axes. And we're going to talk about this a little bit here in a minute, but that's really what we'll talk about a lot in class. Next time, we'll do a couple of problems where we revolve around vertical axes instead of horizontal axes. Okay, so here's a problem where we've got 4 different volume calculations off of the same setup. It says explain and then evaluate each of the following. Find the volume of the solid generated by revolving the region bounded by y equals square root of x and the lines y equal 2 and x equals 0 about the x-axis, the line y equals 2, the y-axis, and the line x is equal to 4. Okay, so I want to show you this on the calculator just to make sure everybody's clear. When we do these things on the calculator, how can we visualize these things? Okay, so first thing that I'm going to do here is I'm going to graph the square root of x. And we are also bounded by y is equal to 2. So I want to make sure I have that on my graph. And I'm going to set up my window here. I'm going to start at 0. I'm going to go out to 5 this time. And I don't need to really, I guess I'll go from -1 so I can see a little bit of the negative region. And let's see if I'm going to go out to 5. Let's just go up to 5. Okay, so this is what I'm looking at. Now, the thing you have to be careful about is which region are we actually describing here? So it says the region bounded by y equals square root of x, the lines y equal 2 and x is equal to 0. So that's actually this region up here. The most common mistake that people make on these volume problems is they're not looking at the correct region. So always take your time on that initial step of looking at the graph and make sure that you're using the region that is described within the problem. Okay, so for part A, it says, let's revolve this region about the x-axis. Okay, so I'm going to revolve about the x-axis, this region. Immediately, I can tell this is going to be washers. And the reason I know it's going to be washers is because I have empty space here between my area and what I'm revolving around. So since there's empty space, I know I have washers. And now let's just go back to this setup and take a look at how we would set this up. So I've got washers. So when I think about what are my radii going to look like in this case, well, my radii, y equals 2 is essentially the upper function here because we've got a graph that looks kind of like this, right? And then we had y is equal to 2 coming across. And this was my region in here. Okay, so my radii here, there's my outside radius. And then here's my inside radius. Okay, so from that, I can tell my outside radius is going to be 2, and my inside radius is just going to be the square root of x. And if you look at this, remember, we're going to do pi r squared minus pi r squared. So my outside radius squared, what I have right here is essentially 2 squared, and the x is coming from square root of x being squared. So in the end, I just did the same thing I did before. It's just that what made this a little bit harder was that we had to go through and we had to graph it on the calculator, and then from the calculator, interpret what the region was. All right, let's take a look at the second one, because this is going to be a little trickier. So the second one says, let's revolve that same region about the y-axis. So I'm actually going to graph this so we can draw on this. So let me graph this again really quickly. We had the square root function. We have y is equal to 2. And notice when I sketch these graphs, they're not perfect. I'm just trying to get this clear in my mind, what exactly is happening. So it's all of this region. And this time, I'm going to revolve about this axis. Okay, so when I revolve about that axis, I am going to get a disk, because remember, we're bounded by x is equal to 0, or the y-axis. So I'm revolving around a vertical axis this time. So when I cut my cross section, it's always going to be perpendicular to the axis of revolution. That means my cross section is going to cut through this way. So I'm going to have a disk, and that's going to be the radius. But notice the thickness of the disk this time is not dx. The thickness, if I measured from here to here, that thickness is measured in the y direction. The thickness is dy. So when I'm thinking about this curve, y is equal to square root of x that I had right here, I want to think about that in terms of y. X is equal to y squared. And the reason I want to think about that in terms of y is because the thickness, the dy, is always the driver in terms of, am I going to set up my integral in terms of x or in terms of y? So my radius this time is going to be y squared. And my cross-sectional area would be pi times y squared, quantity squared. And you can see that then leads to this setup. Notice we went from 0 to 2 because we're essentially using the y-axis as the axis that we are integrating along. So this is some of that stuff that we did with areas starts to come into play here, right? Because this was y is equal to 2. So I started at y equals 0, and I'm integrating in the positive direction up to y is equal to 2. Okay, so you can see it gets a little trickier here when we start revolving around vertical axes. For part C, it says, let's revolve around the line y is equal to 2. Okay, so that's a horizontal line again. So let's take a look at that one more time. I'm going to draw this again. So I've got my square root function. I've got y is equal to 2. This is y equals square root of x. Okay, so now let's take a look at if we were going to revolve about the line y is equal to 2. And you can draw this on here if you want. You don't have to, but I'm showing that I'm revolving around that axis. Okay, so look at your region. This is my region. And my region is actually bounded by y is equal to 2. So when I set this one up, I am going to have a disk. The difference this time, though, is look at my radius. Since I'm revolving around y is equal to 2, my radius is the distance between those two curves. So again, going back to what we did with areas, the distance between those two curves is the upper curve minus the lower curve. So my radius this time for my disk is just going to be 2 minus the square root of x. So notice my setup this time. We've got from 0 to 4, pi times 2 minus square root of x squared dx. And again, I probably would actually have this pi out here in my setup. This was actually a textbook question. They don't always do it that way, but I would plug the pi or put the pi outside, solve that integral out, and then I can get the exact solution. But the big thing here is we're revolving around a line other than the x-axis. So we have to make sure we reference that line when we're talking about our radius. What's the distance from that line to our curve that is essentially bounding where that cross-sectional dimension is coming from. Okay, so, and again, you can see on all three of these, you can see the solutions, the three that we've done so far, the exact solutions. Let's take a look at the last one, the line x is equal to 4. Okay, so we're going to take that region, we're going to revolve around x is equal to 4. Now, sometimes you may not want to graph these by hand, so I just want to show you on the calculator, if you need to revolve around a vertical line and you want to help visualize what that vertical line looks like, let me show you this. So I'm going to go back to my calculator graph. Okay, so here's my calculator graph. And remember, we were going to revolve this time around x is equal to 4. So to get that x is equal to 4 line, I'm going to go back to my main screen. If you hit second and then the program button, there's actually a draw menu here. I know that's pretty small, but it says draw. And option number 4 on this draw menu is to draw a vertical line. So I'm going to choose option 4, and it says vertical. And then it just wants a value here. Where do you want me to draw a vertical line? And we want to draw a vertical line at x is equal to 4 because that's what we're going to revolve around. And now it puts in this line at x is equal to 4. So I'm taking this region and I'm going to revolve around x is equal to 4. Now I'm going to draw this on my paper in a second, but at least you have a way that you can do this on the calculator if you want. And if you need to get rid of that line, you can always go in here and you can hit second and the program button. You can do clear draw. And then when you go back, now it's gone. Okay, so anyway, let's go back to the paper and we'll talk about where the dimensions are coming from when we sketch this out. Okay, so I'm going to graph this one more time. We've got that square root curve. We've got the y is equal to 2. I know that angled just a little bit there, but again, your graphs don't have to be perfect. We're just trying to get the general idea here. Okay, and then x is equal to 4 is going to be right here. Now we're going to revolve about x is equal to 4 this time. And this is a little bit tricky. So remember when we were doing areas and we were kind of turning the graph so that we could visualize these things? This is where that becomes a really important idea to understand. So notice we have this red region revolving around the vertical line. So we have all this empty space in here that we have to account for. That means we're going to end up with a washer. So when I measure my radii, I'm going to have 2 radii here. My outside radius, which I'm going to call capital R, is that one. And you can see it goes from x is equal to 4 to x is equal to 0. So it's always 4 units. But the inside radius is going to be this distance, which goes from x is equal to 4 to this square root curve. Remember, this was y equals square root of x, which is the same as x is equal to y squared. Now, my cross sections are now going horizontally here again. So that means their thickness is dy. So I need to have everything written in terms of y. So when I set up my radii this time, my outside radius is clearly just 4 because it's x is equal to 4 minus x is equal to 0. But for my inside radius, I've got to do the x is equal to 4 minus the curve. The curve here is y squared. So it's 4 minus y squared. So you might think, well, why does this integral look totally different than what I'm expecting? Because you would think it would be the outside radius squared, which would be 16, minus the inside radius squared, 4 minus y squared. Well, it's just because there's some algebra here that happens when you set this up. So in the end, let me see if I can squeeze this in here. You would have pi times the 4 squared minus the 4 minus y squared. And if you were to go through and expand out the 4 minus y squared and combine everything together, you would get what is up here. So that's the algebra you would have to do, but it would simplify down into 8y squared minus y to the fourth. Okay, so in the end, the big thing here is the setup. How do I get the setup? I have to think about the outside radius and I have to think about the inside radius. Since I'm revolving around a vertical line, everything will be written in terms of x. So I've got to get, or excuse me, written in terms of y. So I have to get x in terms of y. And then I have to think about those distances in the same way that we did when we were finding the heights of the rectangles when we were doing areas. Now those distances that we're finding are representing radii for our outside circle and our inside circle for our washer. Okay, so like I said, this is kind of a difficult concept. You're going to have a couple of days on this assignment. So we're going to talk about a lot more of these in class next time. We'll talk a lot more about revolving around a vertical line, revolving around lines other than the x-axis and the y-axis. But the main bulk of this thing is always the same. The kind of the meat of this idea always goes back to a very simple concept. To find the volume, we need the cross-section. We give it a thickness of dx most of the time. Sometimes it's going to be dy when we revolve around a vertical line. And then we're just going to integrate over that region.